Jai Hind, Namaskar. I am Minakshi Kumar, Faculty of Photogrammetry and Remote Sensing Department, which is a part of Geospatial Technology and Outreach Program Group at Indian Institute of Remote Sensing, a premier capacity building institute under Indian Space Research Organization, that is ISRO. In today's session, we will see image processing of ultra high resolution images which are captured by unmanned aerial systems, popularly known as drones. The outline of today's session would be, as we have to discuss about image processing of ultra high resolution images, we should know what is an image, what is a digital image, and what is image processing. We should also discuss about the resolutions and what we mean by high resolution and ultra high resolution images. Then we should see the processing of these ultra high resolution images. If you are familiar with image processing of multispectral imageries, you must be aware that the software or the image processing, we should do at least three basic functionalities: image restoration, enhancement, and most important, information extraction or feature extraction. So we will see the applicabilities of these three basic image processing techniques on ultra high resolution images. For ultra high resolution images, the most applicable method is object based analysis, abbreviated as OBIA. So we will see that in little detail, and we will conclude with few examples on the case studies which are carried with UAV images and other high resolution multispectral satellite images. So to begin with a question that what is an image? Image is a pictorial representation of an object or a scene or a phenomena. There are basically two types of images: analog images and digital images. Analog images are captured by photographic sensors like our good old cameras, where we used to take the photograph on a negative on a film and then get the film developed and printed at a photo printing shop. So those were our analog images. Nowadays, most of us are taking photographs by our digital cameras or even mobile phone cameras. Those are the digital images. Digital images are captured by electro-optical sensors, and they are composed of uh, tiny equal areas called as picture elements or pixels, abbreviated as pixels or pels, and they are arranged in a rectangular array. Now with each pixel, it's associated a number which is called as digital number or brightness value, or a gray level, which is basically a record of variation of radiant energy in discrete form from a small area on the earth. Right? If you see on the slide, the lower digital image which you are seeing is a colorless image. So that is a single layer digital image will always be colorless or in fact grayscale. And if we zoom, the pixel value for each pixel will only be one value. And if you have a colored image, it is actually made up of three layers. The area is captured by the same sensor, same number of rows and columns in three different wavelength intervals, mainly red, green, and blue, and they are displayed in the RGB of the monitor. So if we zoom and look at the pixel values, for each pixel we get a red intensity, a green, and a blue intensity value. Coming to image processing, if we have analog images and if we have digital images, we can do analog image processing for analog images. We do not have much options in analog image processing other than the recoloring, few enhancements which can be done in the photo lab, some applying some color filters and taking reprints. Here the process is not repetitive. Each time that you develop, you will get a different output. The analog and digital images can be visually interpreted, which is known as visual image interpretation, which is basically the act of examining images to identify different objects and judge their significance. For visual image interpretation, we use various elements of interpretation like shape, size, tone, texture, pattern, shadow, association, stereoscopic appearance, resolution, and then we judge the significance and we converge the evidence based on using more than one element of interpretation. Digital image processing, in simple words, is actually the manipulation of the digital numbers in the image for purpose of image correction, enhancement and information extraction. That means my input is an image and output is a processed or an enhanced image. So we basically aim to extract certain unique information from the image by doing digital image processing. Now, since our topic says the image processing of ultra high resolution images, we should discuss resolution. If you're already familiar with remote sensing, then you know the four resolutions of remote sensing. If not, I thought I will just take a few 1 minute to just to refresh the concepts of resolution. Resolution is basically the ability of the sensor system to render the information in smallest separable quantities. Right? In terms of either distance, then it is called as spatial resolution, or a wavelength band of the electromagnetic spectrum called as spectral resolution, the resonant frequency, temporal resolution, and the radiation quantity, the brightness levels, that is the radiometric resolution. So spatial resolution, in a nutshell, it basically determines the size of the smallest possible feature. So basically it is the pixel size and it's described by the instantaneous field of view of the sensor. The spectral resolution is the ability of the sensor to capture data in fine wavelength intervals. So basically we also see how many number of bands are captured for the spectral resolution. The radiometric resolution is the quantization level or number of brightness levels to which the sensor can record the different DN values. Temporal resolution is the revisit capability of the sensor to look at the same area after a few days, hours, etc. So when we talk of high resolution and ultra high resolution, we are mainly referring to is the spatial resolution or the pixel size. So high resolution imageries, multispectral imageries have spatial resolutions varying from 0.3 meters to 4 meters. This nomenclature has been changing since the time the new satellite sensors are being launched. Like in 1999, when Iconos satellite was launched, it had 1 meter panchromatic resolution. It was high spatial resolution. Before that, in 1995-96, when IRIS-1C pan data was there, that was the highest spatial resolution available. So the nomenclature for high resolution has been changing. For multispectral satellite images, we say that the sub-meter to meter resolutions are the higher, to 1 meter resolution we can say is the high spatial resolution. And these imageries are having spectral bands from 1 to 8. That means 1 is the panchromatic sensors, and for some of the satellites it has 8 bands capability also. The image that we are seeing is the sub-meter pixel resolution, Cartosat satellite image. The Cartosat satellite, which has been recently launched on 23rd June 2017, and these were the first images of this, the image capture, multispectral image, which was captured by Cartosat satellite on June 26th for the Doha area. So if we talk of ultra high resolution imagery, the ultra high resolution imagery, we normally say it is captured by the unmanned aerial vehicles or UAVs or drones. Right? Their characteristics is that they have very high spatial resolution. The spatial resolutions are not in meters but centimeters to millimeters. In such images, the geometry and the outline of the objects is very clearly visible. Mainly, they have the images are captured by the digital cameras and they are optical true color composites. Now the trend has also started for multispectral uh, camera onboard UAVs as well as thermal and SAR data or SAR sensors onboard the UAVs. But most common use is for of the optical true color imageries in ultra high resolution imageries. So now I will show you few images captured by UAVs. This is a Trimble sample data set. The image that is being shown here is actually ortho image which was generated. The pixel size is 5 centimeter here and it belongs to an area of Belgium. So with UAVs, as you have been told already, only it is possible to capture small areas at a time. Right? So this is a zoomed portion from the previous imagery. From this part, as previous, the imagery has this, and you can see the fine details that are available. Right? Even the path of the movement of the vehicle is also clearly marked. This is another image of the railway line which was captured by a UAV in the Netherlands, which is actually at the German border, right? And it was captured with a pixel resolution of 2 centimeter. And if we zoom a particular area, we can see the fineness of the image, the rail links as well as the gravels are also visible, the wires, etc. All the very fine details are visible. The with fine details, the problem is the size of the image becomes very large. The volume of the data is too much. Now this is another sample data of UAV. It is for the Hanover Expo Park, which is there in Germany. The data was captured on 11th October 2012. It was captured in 1021 images, right? And for the flying altitude was 185 meters of the drone. The pixel size was 3.5 centimeter, and the coverage area is 1 square kilometer. The each pixel, each image is the 4500 by 3400 approximate size of each image, right? The focal length of the camera was 20 mm. This is the ortho image which is generated. The ortho image was generated at the spatial resolution of 3 centimeters. And since it is an optical true color composite, the image size is quite voluminous. You can see that the image size is 38,000 by 32,000 and there are three different layers. The image shows the layout of this Hanover Park over the Google Earth. If we zoom out to any area of the Hanover Park, which we'll be using in our first subsequent slides also, you can see the fineness of the details, the roads and the road markings, the different type of trees, the different tree crowns in the orchard, and different cars are also clearly visible. So this is the default zoom level here. So you can see that the fine markings on the road and the center of the road is also clearly visible. The different tree types, the different cars and their shadows, the car parking markings, etc. also is clearly visible. In fact, the patch of the road which has been recently repaired is also seen indicated in the image. That is the quality of the UAV image, very high, ultra high resolution, we would call it. So then the processing of these ultra high resolution images also requires certain attention. As you know, for processing a multispectral imagery, there are basically three categories: pre-processing or image restoration, in which we remove all kind of errors from our imagery. Now the UAV imageries are large number of imageries, as you can see, over large number of overlapping imageries. The orientation of each image is different according to the different flight plans that have been the flight planning which has been done. So and also the images which are required from these UAVs, they contain camera and terrain related distortions. So these images are unsuitable for directly for the geospatial analysis. So they are basically the single point perspective. Each photograph is a single point perspective of the Earth's surface. And if I want to use the image as image map, that means whenever I want to use my image for making accurate area, distance and direction measurements, I have to to make an orthogonal transformation here, or in fact ortho rectification should be done to correct the distortions or the tilt distortions, the lens distortions and the relief distortions. For removing such distortions, the orthorectation should be carried out. For this, we require the additional parameters, the camera calibration parameters, the ground control points, the photogrammetric processing, triangulation, generating the digital surface model, and generating the ortho image, which can subsequently be used for further feature extraction. So this is the basic requirement. The UAV images should be ortho rectified to an ortho mosaic. Then the second category of image processing on UAV images is enhancement techniques. Now since we are doing ortho rectification in the resampling process, most of the distortions, most of the radiometric discrepancies are also removed. And enhancements are basically subjective to the image requirement. There are basically three categories of enhancement which we apply on multispectral imagery. They are radiometric enhancement, spatial enhancement, and spectral enhancement. In radiometric enhancement, we improve the contrast of the imagery so that if applicable can on the UAV imagery can also be done. But here, since the flying height is less, the enhancements and the multispectral camera, this entire range of these devices being used, so the less applicability of contrast enhancement here. But spatial enhancement or basically local operations or convolution operations can be used for information extraction, for extracting linear features and boundaries of the objects. The most important component is information extraction, which is applicable on these ultra high resolution images. So before going to ultra high resolution information extraction, we will see again just refresh our memory with what is the traditional image analysis approach and what are their limitations. So with multispectral images or even high resolution satellite images, we can do visual image interpretation, which I mentioned that it is act of examining images to to detect objects and judge their significance. And we use various elements of interpretation like shape, texture, pattern, shadow, association, etc. Now, digital image analysis, the information extraction is mainly classification, and it is pixel based classification, which is basically automatically categorizing all pixels in an image into different land cover classes or themes. So there are two categories of multispectral classification. They are supervised and unsupervised classification. Unsupervised classification is the one where the sample areas are not available to the algorithm. That is, the identity of different land covers to be classified are not known. So it is the computer and the software, the algorithm basically, which groups similarly reflecting pixels, right? Which groups similarly reflecting pixels into unique clusters according to some statistical criteria. It is the analyst who then relabels the spectral clusters into the information classes. As compared to the supervised classification, in supervised classification, the samples are known, right? That means in the study area, some sample areas are known to the analyst, and these are called as training sites. It is the statistics of these training sites which governs the classification process. That is, all the pixels which are either inside the training site or an unknown pixel, its statistics is compared with the statistics of the training sample or the potential class, and it is classified to that class to which it has highest likelihood of being a member. Right? Uh, so the supervised classification or the pixel based classifications can be done in two modes: hard classification and soft classification. Hard classification is one where a pixel is assigned to only one class, whereas there are soft classifiers, fuzzy classifiers, where a pixel has a membership of belonging to more than one class. There are different algorithms for supervised classification. That is, commonly used ones are the parallel pipette, the minimum distance to mean, Mahalanobis distance classifier, and the most commonly used maximum likelihood classifier or MLC classifier. Now, these are the information extraction techniques on the multispectral imageries. What are their limitations? If we do visual image interpretation, my digital image is made up of pixels. And if I visually analyze this, I don't see pixels, I don't classify pixels. Right? So we basically see with our eye homogeneous objects and we judge their significance according by using certain elements of interpretation. Right? Digital image analysis, we use pixels, and pixel is basically an artificial unit, right? Our boundaries of land cover do not end at pixel boundaries. So a pixel basically forms an artificial unit. Moreover, the classification methods, supervised or unsupervised, they use only single element of interpretation, which is tone, right, or the digital value, right. So the other elements of visual interpretation, which the human cognitive principles, that is shape, size, tone, textures, are not used in the supervised or unsupervised classification. So in pixel-based analysis also only, it led to further developments of using advanced classification methods like neural network classification, or you are using advanced layers like texture parameters which are calculated from the image to be incorporated along with the raw data. So with the limitations of this conventional pixel-based classification, we know that there is a technique called as oriented analysis or object based analysis, OBIA, which basically supports the cognitive analysis, that is the analysis which we use in human, that is the human intelligence which we use in visual image interpretation, right. So we can say that it is a form of knowledge driven analysis. The human knowledge can be incorporated in object based information extraction. So object based image classification, one in which we do not work on single pixels. The basic processing unit is not single pixel. but a group of connected pixels which are called as image objects or segments. And these objects or image segments are a group of connected pixels having some common property. It may be color, it may be shape, it may be area, it may be scale, and if it's a video image, it may be motion. So that is an object. So here you can see that this is a very high resolution, 1 meter spatial resolution image which has been segmented, or which has been a group of connected pixels have been connected together to form one region called as image object or a image segment. Now the advantage or comparison between pixel based and object oriented classification is that in pixel based classification, the prerequisite is that the image has to be error free. We basically perform the atmospheric corrections on the image, right? And here in object oriented classification, we can directly apply segmentation onto the image. Now, the pixel based classification are only based on the spectral characteristics of the data, that is only the tone. Here, besides the raw data, we can incorporate additional layers into the classification, such as the elevation model, the different texture parameters, the different transformation, contextual information, previously classified land use land cover map, the derived products from the digital elevation model like slope, aspects, etc., can be incorporated into the classification system. So in pixel based classification, one pixel, the classification is done at one time only. Whether it is hard classification or soft classification, it is done at one time only. Whereas in object oriented classification, we have the possibility of applying a step by step classification onto the image. Then for smoothing the results, normally in pixel based classification, we apply the mode filters to reduce the distortion. Here, because already you are segmenting the image first, it is into homogeneous regions, we do not need to filter the image after segmentation or after object oriented classification. So when we say the object oriented, and also the important thing is that object oriented image classifiers use soft classifiers, that is fuzzy logic, and not simple hard classifiers, right? So for understanding object oriented classification, we should first understand objects. We should first understand how objects are created. So objects are created using the image segmentation. The image objects or segments are created using image segmentation, and that is why we should first understand what is image segmentation before understanding the further part of object oriented image analysis. Excuse me. Image segmentation, basically, it's a process of partitioning an image into non-overlapping homogeneous regions of related content. Right? So that means basically we are partitioning an image into homogeneous regions. That means we should test some criteria for homogeneity and non-overlapping. That means my regions should be disjoint. They should not be overlapping. So they are regions of different statistical behavior called as segments. So basically segmentation not only deals with region segmentation, I can partition my entire image into regions. Like here in this example, the partitioning is being done based on the color. I can also partition my image into linear structures or into shapes. Like here in the next slide. So I can partition my image into boundaries, right? Connected boundaries will form a region. So I can also partition my image. I hope the image is clear because here it is quite dark. The outline of the image objects was created here. Then here again it's an example of region segmentation, that is the textured cloth which has been the entire image has been segmented. Here again a high resolution world view image of 0.5 meter resolution has been segmented and required information has been extracted. So how to segment an image? So my segmentation algorithms are based on two basic properties of intensity values. So see, first we are talking about intensity values only because that is the main feature that I have. So the algorithms are based on two basic properties, that is discontinuity and similarity. So the discontinuity is to partition an image based on abrupt changes in intensity, right? Such as the edges in the image. And the second category is basically partitioning an image into regions according to the similarity criteria. Right? So the different methods, so region based methods are more commonly used for image segmentation, right? Whereas boundary based segmentation are mainly used for feature extraction, for especially the features which are based on the linear or the linear features or the boundary based, the edges. The different methods of region segmentation are thresholding, clustering, split and merge, region growing, multi-resolution segmentation, or also called as object-oriented classification segmentation. Then in boundary-based segmentation, we have methods which are based on the detecting edges from the satellite image or the high resolution, ultra high resolution images, and basically convolution filters like Sobel, Robert, Kirsch, and Laplace find themselves in this category. There is also watershed segmentation technique which determines the watershed boundaries for segmentation. So we will see some of the techniques. Thresholding is the most simple technique for image segmentation. It is basically a gray level remapping operation which basically maps a gray value image into a binary image, right? A gray value image into a binary image. So as you see the example here, this is the thumbprint on a paper. This is the rice granules on a black cloth. They are basically bimodal images, right? There are two dominant modes, one for the black region, here in this case the fingerprint, and the other is the white background. Here it is vice versa, here the black is the background and white is the object, right? So thresholding means determining a value and separating the image into zeros and ones into the binary image. Like for example, here there are two dominant modes. So it would be most appropriate to take a threshold in the depth and all the values below this threshold are assigned as black and all the values above are assigned as white. So this is the result after segmentation. That is, it has converted the image into bitmap. Here also the same thing, the threshold has separated or had segmented the image into rice granule and black cloth. The selection of the threshold is very important because it is based on the threshold selection only that you can see that my size of the rice granule will change unless my threshold is optimal. But remote sensing data is not so simple. It is not bimodal in nature. In fact, it is multimodal in nature, right? So this is similar to a typical remote sensing or the multispectral uh, image histogram, which has large number of peaks. Large number of peaks means more different classes, more features present in the area. In again for thresholding method it would be same, that is to separate out the peaks, take the threshold in the depths, and here not one threshold but we will have to take more thresholds or multimodal histogram. Apply the multimodal thresholding on our ultra high resolution drone images. For the Hanover area, we have taken a small subset here, and that has been a multiple thresholding has been applied, and you can see that the even in the road we are getting at least 3 categories of the color for the thresholding. The another segmentation technique is clustering, and it basically the algorithms which are under clustering are k-means or migrating means and mean shift. So all these algorithms refer to same clustering procedure. Clustering is when the algorithm is trying to find out natural groupings from my data set. So here, like you can see that here it is feature space has been drawn, a two-band feature space, right, and some few pixels have been marked. If the purpose is to split them into two different clusters, so the cluster centers are identified, then all pixels are the distance of all pixels to these two cluster centers computed, and the pixel will be labeled to the closest cluster center, right? And it is iterative procedure. So in after the first iteration, the cluster statistics are recomputed. The cluster center, if it changes, the procedure will be repeated. So the procedure will converge only once the cluster center does not change by certain threshold percentage, or you have defined a number of iteration levels they have been achieved. So this is the result of applying clustering techniques again on our ultra high resolution data sets. So this image is having 12 clusters, the image is having 6 clusters. So basically grouping of pixels. Now both the methods, thresholding or clustering, the disadvantages, again we are using only one parameter, which is tone, right, which is only tone. Then coming to region based segmentation. So here we are grouping pixels which are having similar values by using two approaches, either a bottom up approach or a top down approach. A bottom up approach is a region growing approach where we give either manual or automatic seed points and automatically grow the region, right, until the entire image is segmented. The top-down approach is the opposite. It starts with the whole image and it goes on partitioning the image in, into homogeneous segment until the image cannot be split. So we will see there is a variation of region splitting, that is split and merge algorithm, right, where after each iteration the homogeneous regions are merged back. So region growing algorithm is basically a bottom up approach where we start with one pixel of a potential region and grow it by adding adjacent pixels till the pixels that are being added are too dissimilar. So I can give large number of random seed pixels or start with the first pixel, grow the region. So that means the second pixel region will be automatically generated by using the statistical tests. So statistical test could be very simple, like simple range of DN values or mean and standard deviation can be used as a statistical test for determining whether a particular pixel will be added to the region or not. So here, like for example, I have zoomed the Hanover image. The road part, I've taken one seed pixel, and wherever the values were similar, it has grouped them into one region. So this is the region segmentation or region grid segmentation, and this one category has been classified. So this was manual seeding, just to demonstrate. The splitting method is opposite to region growing, as I was mentioning. It is a top-down approach. It starts with the entire image, and if the image is not homogeneous, it will divide it into 4 sub-images, right? And the procedure will be recursively executed until the image is segmented into homogeneous regions. Now the disadvantages that if you are only going on splitting, it will show artifacts at the boundaries because regions which had reflectance, you have not grouped them together. So a variation of splitting method is a split and merge method, which is after each splitting the homogeneity test is done and the regions which are homogeneous are grouped back. So both the region growing and split and merge methods are using not only tone but the adjacency. That means the pixels data, the neighborhood of pixels is being considered in both. So that means not only spectral information but as well as the spatial location of pixels is being considered for segmentation. So here, yeah, like you can see that the images on which the only the region splitting and region split and merge is applied. So splitting the artifact is visible here. Yeah, the same regions which have similar value are appearing pixelated, and here it is a smooth region. Right. So these were the 4 basic methods of segmentation. Now multi-resolution analysis or multi-resolution image segmentation or object-based image segmentation is basically a kind of region growing technique only. So it is a bottom-up region merging technique. It starts with one pixel objects. It starts with the assumption that all pixels are objects, and then in numerous steps these smaller objects are merged into bigger ones to form regions. So the merging decision, it is basically based on a local homogeneity criteria which describes the similarity between the adjacent objects, whether they should be merged or not merged. So if the smallest growth exceeds the threshold, smallest growth, that means the adding a pixel to a region, if it exceeds the threshold which is defined by a certain parameter, the process will stop, right? So it is done in iteration. So throughout this segmentation procedure, whole image is segmented and objects are generated based upon several adjustable criteria of homogeneity which are described by color and shape. So there are basically 3 main parameters: scale parameter and color and shape parameter. And this multi-resolution image segmentation is also called fractal net evolution approach. It's an approach which has been implemented by Ecognition, or basically now it is called as Definian's developer software, a powerful software for object-based image analysis. So it uses, as I was mentioning, the scale parameter, right, which basically determines the size of my image objects. If I have a small scale parameter, I have very small objects. I have a large value for the scale parameter, I have bigger objects, bigger regions. Right? Then the composition of homogeneity is described by the color and the shape criteria. Color, if you are giving so like said, let's say 0.5 importance to color, that means I'm giving equal importance to shape. So I can change the importance of shape and color based upon my resolution of the data, the spatial resolution of the data, and the spectral resolution of the spectral information in the data set. The shape again is defined by the smoothness and compactness criteria in the Ecognition software. So like here, this image, the same our the Hanover subset has been segmented using the multi-resolution image segmentation using a scale parameter of 35, and you can see that the when we are looking at road, we are seeing that there are large number of image segments which should have been merged. So that means I should have taken a larger segment scale parameter. But when we look at these cars with this scale parameter, the bonnet, the windscreen, and the top of the car, which are actually three different objects because by the angle it is visible, so they have been segmented correctly. And even the shadow has gone into a separate class. And in the road also, with this scale parameter also, the road markings have been separated. So this is segmentation is done, image segmentation in recognition software. So whichever technique you use for segmentation, whether you use thresholding or clustering or region growing or split and merge technique, the ultimate aim is to attach the information utility. So the segmented agents can then be classified either using a simple standard nearest neighbor classifier approach. That means we supply the samples that this particular image object is a road or this particular image object is a tree, and it is classified based on samples. Or for the image objects, we can generate various fuzzy rules by integrating other parameters other than the only the raw DN values, right? We can incorporate the texture parameters, we can incorporate the geometrical parameters, in addition to the layer, and many other contextual information can be incorporated into the forming the fuzzy rules for classification. Right. So here we can see the comparison between the maximum likelihood classification uh, on the ultra high resolution images and effect of the object based classification on the ultra high resolution images. So here in maximum likelihood classifier, you can see that you see these even after the classified results, it appears as if it is salt and pepper noise, and there are many misclassifications, whereas the number of misclassification chances are less in the object based classifier. Now, these were region based segmentations, and as I was mentioning, the boundary based segmentations are mainly used for extracting features and making the boundary maps around different objects. So, here on that same Hanover data set, different convolution filters have been applied to extract the road boundaries, the tree boundaries, the boundaries of the car. So different boundary based segmentations can be used if my purpose is only to extract the edges out of the data set. Now there are different softwares which are available to do this object based image analysis. They are the ADAS Imagine has ADAS Imagine Objective. Envy has its feature analyst. There is Spring to do object based analysis. There is Parbat to do object oriented analysis. Recognition is a very popular software which is mainly for object based image analysis. And if somebody is a programmer, you are from programming background, you can write your own programs to segment the image and then later to classify it. Now, some of the few case studies which have been done, I know you have been told many case studies in past 3 days, right? But here I have tried to include those case studies which are done at TIRUS, right? Using either UAV datasets or high resolution multispectral datasets. So over the Hanover area, it was attempted to extract very small objects like cars, detecting and discriminating between cars and detecting their shadows, extracting the different roads and the different road markings on the extracting different trees on the UAV Hanover dataset using again the object based image analysis approach by framing fuzzy rules over the data set, incorporating textures and geometrical and contextual features. Now, this image is for Dehradun area only, nearby to Dehradun area. The number of images were captured by UAV drone, and the GCPs were also collected using differential GPS. The photogrammetric process was done to generate the DM and ortho rectify the image, and after then the image was segmented and classified to extract the different field boundaries and trees in the data set. So since it is a UAV data set, it was we had the digital elevation model. So we use the digital elevation model as well as the derived products from digital elevation model incorporated along with the layer values and texture values to extract field boundaries and the extract different trees in the area. The another study which is not on UAV but it is on very high resolution data sets from LIS4 to Iconos. This work has been carried out by extracting agriculture field boundary using object based image analysis approach. It was done on the agriculture farms of Hisar and Pantnagar agriculture fields. The image was segmented. Fuzzy rules were developed for extracting the field boundaries. If there was any problem in the field boundary, like here overlaps in the field boundaries, it was refined using the snakes algorithm, and the accuracies were high in the areas of the regular farm, and it was low in the area of Saharanpur where the farms were very small, and here they were regular farms, it was irregular farms, personal farms. So other studies which have also been attempted on very high resolution data sets, Worldview 2 data sets and QuickBird data sets of 0.5 meters merged resolution, is extracting buildings and roads on the data set, and using the high resolution approach, the accuracies achieved are quite good. This is the case study again done on Worldview 2 dataset, 0.5 meter spectral resolution. Here in additional the digital surface model was available from high resolution LiDAR dataset. So that LiDAR dataset DSM was also incorporated along with the raw data for a part of San Francisco to first basically classify all the objects in the area and especially extracting the buildings and the roads to be overlaid over Google Map. So here it was possible to differentiate between the roads and flyover because of the DSM, and some of the building discrimination between buildings, apartments buildings and single floor buildings was also possible due to high resolution LiDAR DSM. So it was possible to include few case studies only here, and I have not included all the case studies that have been done with very high resolution data sets because of the time limitation. So this is all from my side. Now I am open to discussion. Thank you for paying attention.